Now in this example, we want to find the line integral over the curve where the curve is drawn over here. It said the path shown, but it didn't show a path, but there it is. It's that curve right there. And our function is f of x y equals x plus y. So you can see this right here. Right? This right here is your f of x y. That's x plus y over your arc length, right? ds, or section of arc length. All right, so unfortunately for us, we're not going to have one function for over here. This is a piecewise function. It has a sharp point. So we're going to have to separate it into two sections. We're going to call it section A over here on the left, and then section B on the right. Okay, so let's look at section A. Well, first off, we need the curve for that section. So we need to know what it is. We're going to define it as r of t equals, and of course it's always best to just use x equals t, and then we need to know the equation of this line. But of course this goes through the origin and goes through two 2's, so that's a slope of 1, right, up 2 over 2. So slope of 1, and it goes through the origin, so that's just y equals t. Right, or sorry, y equals x, and therefore, right, if y equals x, then t equals t. Now, this is going to be from 0 is less than or equal to t, which is less than or equal to 2 on this one, because we're going all the way to x equals 2. Okay, so then the line integral for this piece of it would be from 0 to 2, and then where we have x, right, this value is our x now, and this is our y. So this is x of t, and this is y of t. All right, so it's x plus y, which is t plus t. And then we're going to multiply by the magnitude of the derivative. Oh, we'd better find that derivative. R prime of t would be 1, 1. So we're going to multiply by the square root of 1 squared plus 1 squared dt. All right, so this is the integral from 0 to 2. That's 2, right? This piece right here, that's the square root of 2, sorry. So that's the square root of 2 times 2 t, right? So this is 2t right here. Right, 2 times the square root of 2t, and then I'm integrating that with respect to t. This particular one's so easy I can do this in my head, right? Because this is a constant times t. So that'd be 1/2 t squared, so that's square root of 2 t squared from 0 to 2, right? Because the half would cancel the 2. And so then that's 4 square root of 2. All right, great. Part A is done. All right, let's do part B, and I'm going to have to fit it in over here. All right, now part B, I need to think about this equation of this line. So this is y equals x over here. This is negative x for the slope plus 4, because if I went all the way back, it would go to 4. In other words, you could also just use 2 points. You know it goes through 2, 2, and 4, 0, and you can find the equation of a line because we've all managed to make it through Algebra 1. Okay, so that means that my curve now on this side, r of t, would be equal to t and then 4 take away t. I'm just going to rewrite that with the 4 in front. And that's going from 2 is less than or equal to t, which is less than or equal to 4. All right, well, we know we're going to need the derivative, so I might as well find it right now. That is 1 and negative 1. Okay, so the line integral is from 2 to 4. And then f of x, y is x plus y, but my x for this section is over here. This is x of t. This is y of t. So I'm going to take t plus 4 minus t times the square root of 1 squared plus negative 1 squared dt. Well, this is just 4, right? So I'm integrating from 2 to 4, 4 square root of 2 dt, which is 4 square root of 2 t, where the t goes from 2 to 4. which is 4, take away 2, which is 2. So this is 8 square root of 2. So the total integral, right, from beginning to end of that curve, x plus y over that section of the curve, right, ds, is equal to 4 square root of 2 plus 8 square root of 2, which would be 12 square root of 2. Now, in our next example, let's get a 2 for 1. Let's find an application problem and do 3 dimensions all at the same time. Won't that be fun? Okay, so I'm just going to pretend, by the way, that this delta is grams per centimeters cubed, x, y, z in centimeters. Just assume. That's in centimeters, by the way. It looks like it's one word, but it's in centimeters. There we go. Just for fun. Okay, so let's look at that mass function, shall we? All right, mass is the integral over this curve, right, this line segment, of our delta function, ds. All right, so that will be equal to the curve, or the integral over the curve of x, y over z ds. All right, so mass, we've learned a long time ago, is the integral of density. Wonderful. All right, we need to figure out this curve, and we're not going to draw this because this is three-dimensional, so that would be a real pain. So we're going to have to just kind of look over here. All right, so let's consider this curve. I'm putting curve in quotes because it's actually a line segment, right? So we're assuming a straight line from one point to the other. Right, from 141 to 363. So now we have to remember several chapters ago when we learned how to find vector valued functions for a straight line from one point to another. Okay, so position function. The position, or excuse me, not position, the direction. So the direction vector, v, is terminal minus initial. So it's 363, take away 141. Remember terminal minus initial? It was a while ago. It all comes back in this chapter. All right, so that would be 2, 2, 2. All right, then I'm going to take my point P and I'm going to make it a vector. And again, the most common way is to use this point, the original point that you're coming from, you're starting. Otherwise, you have to fiddle around with it and it's more of a pain. So we're going to make it 1, 4, 1. There we go. And then we're going to put these two pieces together and make our position function. So our curve in vector valued function form would be 2, 2, 2, our direction vector, times t, plus our point, 1, 4, 1, which would be 2t plus 1, 2t plus 4, 2t plus 1. There is our position function. Now keep in mind, this is now x of t, this is now y of t, and this is now z of t. It doesn't really get much trickier with 3 dimensions. It's just more work, right? But it's not harder. And it's also harder to understand, but we're not drawing it. Okay, so then we know we're going to need the derivative, so we might as well find it right now. But remember, your derivative is your slopes. It's your position, or excuse me, your direction vector. So it's just 2, 2, 2, right? Because the 1, 4, and 1 don't have any derivatives. The derivative is 0. Okay, so now we're ready to go back to the mass. So the mass is equal to the line integral. Now, we didn't put in t values, but we should. I should have written it right here. 0 is less than or equal to t, which is less than or equal to 1. Now, how do I know that? I need to be able to substitute in these values and get the 2 points I had. So if I put 0 in, I would get 1, 4, 1. If I put 1 in, I would get 3, 6, 3. Okay, so I'm going from t equals 0 to t equals 1. Again, you don't have to write the t equals, but I find it helps at this stage to keep track of what we're doing here. All right, then it was x times y over z. That was our function, x times y over z. X is now 2t plus 1. Y is now 2t plus 4. Z is 2t plus 1. And then instead of ds, I would multiply it by the magnitude of 2 squared plus 2 squared plus 2 squared, right, the magnitude of my derivative, and then dt. All right, well, luckily for us, this is going to be pretty simple because those drop away to 1. And then this is the square root of 4 plus 4 plus 4, which is the square root of 12. And that's 2 square root of 3, right? Because 12 is 4 times 3. Okay, so this becomes 2 square root of 3, integral from 0 to 1, 2t plus 4 dt. And that's an easy enough integral that we can do this without a computer. Only if I can write. There we go. So 2 square root of 3. And then this is t squared plus 4t from 0 to 1, which is 2 square root of 3 times 1 plus 4 minus 0, which is nothing. So it's 10 square root of 3. Now, what would be the unit? The unit, because this is mass, would be grams. We will have taken care of the centimeters with all of this, right? So that will get taken care of in time, and all we'll have left is grams. So there you go. You have your application, and also you see how to do it in 3 dimensions. It just adds in one extra layer of work in terms of finding the z. And then, of course, the derivative for that as well.